And I think I'm going to start by introducing our first speaker, which we kind of went with maybe the distance. So we have Dr. Predo Encarnacao. Pedro is an assistant professor and also an affiliate at the Universidad de Católica Portuguesa. So Pedro's main research is on robotics and assistive technologies, and he uses robots as tools to support manipulation for children with neuromotor impairments. Pedro served as the co-chair of a major pan-European research network called Play for Children with Disabilities. In that network, there are more than 100 multidisciplinary researchers and practitioners that are working towards enabling play for children with disabilities. So Pedro is known to us for a few reasons as well. So he's a co-author of a few books. The ones to mention are Guidelines for Supporting Children with Disabilities Play, Methodologies, Tools, and Contexts. And that's an open access. You can download it. I downloaded it this morning. It's an excellent book. It's published in 2018. Robotic Assistive Technologies, Principles and Practice, CRC Press, 2017. And recently working with Albert Cook, who's a prominent researcher in University of Alberta in Edmonton, and Janice Polgar for the 5th edition of their seminal book on assistive technologies, Principles and Practice. And again, that's published by Elsevier 2020. So please join me to welcome Pedro for the first panel start. Thank you.
Thank you so much for your kind presentation. So hello, everybody. My name is Pedro Encarnacao. I would like firstly to thank the organizers for the invitation to be here. I will briefly talk about the potential of robots to enable play for children with disabilities, a very appropriate theme for the World Children's Day that we are celebrating today in Portugal. So I will start by setting the context, mentioning the Ludicast action, and addressing what is play, children with disabilities and play, barriers to play, toys, games, and play spaces, and then I will discuss the role robotics may have in play. I will fly over the slides, but it is really just for introducing the topic, so we can discuss it further afterwards if you find it relevant. Goldie was a cost action active between 2014 and 2018, shared by Professor Sornella Pesci from the University of Bergamo. It was a pan-European network involving a truly multidisciplinary team of more than 100 persons from 32 European countries. In Ludi, Play for Children with Disabilities was at the center of all activities, with all different disciplines contributing with their perspectives to the topic. We aimed at collecting and systematizing existing knowledge, developing new knowledge, and disseminating the best practices with the overall goal of spreading awareness on the importance of giving children with disabilities the opportunity to play. Much of what I'll be talking today comes from the work within Goldie. But what is play? In many publications, we see play defined as what we acknowledge as play. But without a definition, how can we develop the scientific area? How can we compare different studies if they do not share a common definition of play? How to develop technology to enable play without knowing what is play? In Goldie, we adopted the definition by Garvey. Play is a range of voluntary, intrinsically motivated activities associated with recreational pleasure and enjoyment. The main characteristics of play include free choice, process-oriented with no other goal than the pleasure of play, active engagement, among others. We should have clear in our minds the difference between play-like activities, activities that use play to achieve therapeutic or educational goals, and play for the sake of play, with the characteristics mentioned before. Even if just for fun and recreational pleasure, play is not a waste of time. It is important for children's well-being, and even without being controlled by an adult, it is instrumental for child development. And play deprivation has been associated to anxiety, frustration and passivity, decreased sense of self-efficacy, decreased self-confidence, decreased satisfaction, and play deprivation ultimately leads to learned helplessness. But do children with disabilities play? Children with disabilities are, first of all, children. And play is the main occupation for children. For children with disabilities, besides the contribution to their well-being and development, play can also provide opportunities for inclusion. All children need, want, and can play. And you know what? Play is a right enshrined in the United Nations Convention on the Rights of the Child in its Article 31, and in the Convention on the Rights of Persons with Disabilities in Article 30. However, children face many barriers to play, including lack of recognition of importance of play, unsafe hazardous environments, resistant to children's use of public space, balancing risk and safety, lack of access to nature, and the list goes on. Pressure for educational achievement, overly structured schedules for children, neglect of Article 31 in development programs, lack of investment in cultural and artistic opportunities, growing role of electronic media, commercialization of play. We all know that children use toys and games to play and that they play in different spaces. When thinking about children with disabilities, the issue of the accessibility of toys, games, and play spaces comes into play. Should they all be 100% accessible? We should keep in mind that play occurs in the thin border between boredom and frustration. Too much challenge leads to frustration. Too little challenge leads to boredom. Toys, games, play spaces should be chosen according to the capacities and interests of the play participants in order to enable them to experience playfulness. The play value comes from providing opportunities that children can access and use and wish to use. They should provide the just right amount of challenge, and probably they won't be 100% accessible. Especially if you think about play as an opportunity for children with disabilities to interact with typically developing children. You need toys, games, and play spaces that offer the just right amount of challenge for all. This was perhaps a too long digression through play, but I believe it is necessary so you can understand if there is a role for robotics in play, or if robotics is just a hype that will fade away to give way to a new fashion technology. So, is there a role for robotics to support play for children with disabilities? Robots can perceive and act upon the environment. They are able to take decisions. With robotics, toys can come alive. Robots can attract attention, keep the child engaged, adapt to the child, providing always the just right amount of challenge. But we need to be very cautious when developing robotic tools to enable play. Robot autonomy may lead to unpredictable behavior, thus removing a feature that research has shown, for example, children with autism spectrum disorders value. Another pitfall we should avoid is having a robot fully controlling the activity. Remember, if the child is not in charge, it is not play. There are different challenges to address when developing robots to enable play for children with disabilities. How can they provide the just right amount of challenge, keeping the child engaged, not frustrated because it is too difficult to interact, not bored because it is too easy? In order to have a robot adapting to the child, what variables should be observed? For example, time to react, but some children, due to their conditions, require more time. I believe these applications call for robots with different levels of autonomy, from teleoperated that can be used through Wizard of Oz methods to fully autonomous. Should there be different discrete levels of autonomy? Should there be a continuum? And how can we build a complex system that is very easy to use and that can survive children's use? Remember the beginning of this talk. If it requires an adult always supervising and instructing the child, it will not be play. Different robots may be developed. Here you see a Lego Mindstorm robot that was adapted to be controlled through an augmentative and alternative communication software. By controlling the robot, the child is able to manipulate educational items or toys. This is a small vehicle enabling playful mobility. We're not talking about teaching a child to drive or providing functional mobility. We're talking about giving the opportunity for a child to playfully wander around, exploring proprioceptive feedback or exploring the environment. It was developed by Anditech, a Portuguese assistive technology company led by Professor Luís Azevedo, and is being used by children with cerebral palsy in rehabilitation centers. Sorry for that. This is an example of a soft robot that children can freely interact with. It was developed at Polytechnic of Milano by a team led by Professor Andrea Bonarini. It is being used with children with autism spectrum disorders. So in conclusion, I would like you to keep in mind that play characteristics include being a child-led activity, freely chosen, with no other goals besides the fun of playing. Play-like activities with therapeutic and educational goals are important, but do not substitute play for the sake of play. Play is a right for all children. Toys, games, and play spaces need to provide the just right amount of challenge. Robots have many characteristics that make them ideal to support play, namely the potential to adapt to the child needs. But we need to keep in mind what play is in order to not jeopardize the play experience. From a broader perspective, we need to strive for a new culture of play for all, for a society that recognizes the importance of play for the sake of play for all. Thank you so much for your attention.
Thank you very much, Pedro. It was really engaging talk. This is really nice. I think we can quickly, maybe I have one question. Maybe I can't wait asking that question. With the computer games compared to the old times where most of the games and plays were physical and real objects, the computer games, there's tendency for children to go that way and sometimes being passive or even being active on the brain side, not physically. Do you think robots may present some opportunity for that and particularly for children with disability?
I think so. In my experience, children are always very drawn to robots. So they love robots. They like to interact with them. Actually, when I introduced these robots in regular classes where there was a child with disability, it was funny to see that all of a sudden that child that was very often, unfortunately, in a corner just watching the others doing their activities, that child began to be the center of the attention because she or he was using this cute robot in order to perform the same activities that the others were doing. So I do think that robots have the potential to take children away from those computer screens or from all those screens and do some physical activity, well, at least watching something physical and having some physical toy to play with.
Definitely. All right. So thanks so much. For anybody who has any questions, you can just send them to the chat, and then we'll ask those questions in the interactive part of the session at the end. We're going to go to our next speaker, who's Dr. Lois Frankel. Lois is an associate professor and past director of the School of Industrial Design at Carleton University. Her human-centered design research applies a sensory anthropology perspective in the areas of design and aging and disability. She focuses on people, sensory practices and perceptions in every interactions with products, and conducts research and design for improving practices related to balance, communication, mobility, memory, and cognition in areas as diverse as cooking, rehabilitation, shopping, socializing, and wearable technologies. Her early research project with Elizabeth Breuer Hospital, which is a rehab hospital in Ottawa, has now grown into a recently announced Breuer-Carleton partnership. Lois is on two major Answer Create grants with focus on accessibility and user experience. A very special note for today, actually, because Lois is our colleague from industrial design. So Lois is actually retiring after 27 years of working at Carleton this month. So I thought it's good to mention that. And you know, she's been the professor there, training a lot of students, and also being the director of the school for quite some time. She has numerous achievements related to the cause of this event. So it was pretty good idea to actually invite her to give us a talk today. And she has trained many of even on the engineering side, many of our engineering students on inclusive design and accessible design. And our students, for you, Lois, to know that they're using those principles that you teach them in the course in our research, and I'm grateful for that. And maybe I need to take your course at some point, if it's not too late. You're teaching it again in your retirement time. But anyways, thanks, Lois, for all the services you've done to society and Carleton in particular. And we're waiting to hear your talk today. Thank you.
Thank you, Mustafa. I'm just going to share my screen. And yeah, I'd love to see some kind of thumbs up that you can see my screen. That would be great. Good. Okay. So this afternoon, I'm here to tell you about the value of gaining slow insights into assistive needs. And I'm going to do this by using 3 different projects to illustrate my points. I have to get set up here, though. Whoops. Now, of course, I've gone too far. In industrial design, we may begin a design project thinking we're going to solve a specific problem that has been identified by someone else. So in this case, you can imagine the problem is related to skiing. But before we can design a solution, we really need to know we understand the problem. We need to find out about the context and make sure we're looking at the right problem. Sometimes the problem's not clearly understood. For example, in this case, Lindsay's initial goal was to improve ski equipment for skiers with disabilities. And here you can see 3 different skiers who are tethered to volunteers. And I'll explain this a little bit more. So she began to work with the Canadian Adaptive Snow Sports and volunteered as an assistant for a skier from early January, from January to early March 2020, of course before the lockdown, thank goodness. She had an approved ethics protocol, and what she was doing is what we would call participant observation research. And so she was trying to understand, well, what is the problem space? She spent months doing this. And as designers and engineers, we may all be thinking right now, do we have time for these months of hanging around or doing ethnographic observation? And we might think, let's just get the stats and get working. Well, the true answer is no, you do not have the time. But if you don't take the time, you may not be solving the appropriate problem. Context matters, nuances and behaviors matter. All design problems are part of a larger picture. It takes time to understand what's going on. So here, I'm behind the camera, and I'm on a trip with Ben, who is one of my participants in a balance study. We are getting into his car, driving to the mall and walking before the shops open, which he does 3 mornings a week. I'm especially interested in how he uses his walker or his rollator to maintain his balance, and particularly looking at what he's holding onto at every point along the way. This is called ethnographic research, or a type of ethnographic research, where we go into the field, which is actually wherever our end users are when they're engaged in their activities. We spend time with them in groups or separately, and we collect qualitative data. Even if we think we know what the issues are, we need to observe carefully. This process is called making the familiar strange. It refers to the effort of the researcher, in this case me, to continually question the grounds of the conventional, examining the obvious that is so taken for granted by cultural insiders that it becomes invisible to them. Okay, and this next set of pictures, is a project that Alicia Stewart undertook in 2017 and 18. She was wondering how the artists at a local studio for artists with developmental disabilities could use adaptive equipment to make it easier to do some of their artistic activities. Alicia spent at least a day a week for several months hanging around with the artists at work, participating with them in a way that enabled her to observe and gather data about how they work. The paintbrush you see pictured at the left was key to her findings, as were the workstations, which you see in the center, and of course, the way the artists were working on the far right. In each of these three projects, we used tools for collecting our insights. We were systematically trying to pay attention to as much as possible. But it helps to have some guidelines for what you want to pay attention to. We noticed, for example, many of the aspects listed in this first column. What is going on in the space? Who are the actors? What are they doing? What activities are taking place? What objects are they using and how are they using them? What acts and actions are involved, and so on. So across the top of this chart, or this table, you will see 5 different methods represented, and each of them is described below. So that's a different set of guidelines depending on what it is that you hope to be understanding. After that, this is Alicia's affinity diagram, which is basically a set of Post-it notes that she used to organize her observations. Across the top, you'll see 7 columns here, and each of them identify an aspect of what she observed. But the last 3, which you can see in a little square, were especially rich, and she outlined these with a comment. These areas seem to hold most of the autonomy issues. Now, she wasn't looking at usability issues, so this is important. This comment is a social cultural observation and not yet a definition of the design problem. However, by this point, she had begun to refine the problem area, or what we sometimes call the opportunity space. After Alicia, Lindsay, and I began to recognize patterns in our data, whether it be the participants' experiences painting, skiing, or walking, we could use a table like this one from Kimball and Juliet. Each row here identifies a dimension of insight. They're all a little bit more cultural and social, but we were asking in the first one, well, what's the issue? Who is it a problem for? What social cultural factors shape this problem? What evidence do you have that it's a significant problem? And can you think of this problem in a different way? So can you reframe it? According to the authors, Kimball and Juliet, a tool like this enables the design researcher to narrow down from a rich picture about complex interconnected issues towards a key issue which could be improved on. We then go on to develop tools for engaging with our participants to learn more from them. In this case, Lindsay used this particular tool, which was a map of a fictitious ski area. And she wanted to get their understanding about their barriers when accessing the ski area and also when skiing. As I may have mentioned, I hope I mentioned that the skiers were mostly either skiers with disabilities or people who are assisting them or work with them. And in the end, she ended up with a set of recommendations for better accessibility at ski areas, part of which included the concept of an interactive online map, which she had also started by using with her discussions with participants. In the case of Alicia, she began to iterate possible solutions to artist challenges with cleaning paintbrushes, something that seems rather simple, but it's amazing how an artist can destroy a brush if they don't clean it properly. So first of all, you'll see sort of up in this top left area, she did sketches. She then developed prototypes, and then she did usability testing, which is something I think we are more familiar with later in the design development process. And so this enabled her to start to develop an understanding about what the issues would be and how she could design a container to avoid the issues she had observed. So some of those issues are the softening of the glue with too much water, breaking the bristles while cleaning them, and leaving the paint to harden in them. Ultimately, her containers would help the brushes last longer, reduce expenses associated with the program, and this was part of a much larger solution to the problem. So lastly, I want to talk about my case. It became clear that the one perfect rollator that a client purchases is not suited to the variety of locations people find themselves in. So they often have more than one, and not all of them are adjusted to their bodies. The saying that you can't see the forest for the trees may be an apt metaphor for the way many of us approach design. We see the details of the problem, but sometimes we miss the larger context. Ethnographic research methods contribute to the design of better assistive devices by encompassing the bigger picture. So my balance study highlighted situations where we designers have not yet seen the forest, in which our products do not fully optimize the range of challenges people are facing. For example, a perfect rollator would perhaps be more suited to a family of related products, or have interchangeable parts for different situations, or communicate with other assistive devices when it's time to make a transition from one to another. The 3 projects that I have quickly presented today were deeply influenced by hanging around and slowing down enough to understand what people's lived experiences involve. My message here is that there's great value in hanging around and gathering slow insights into assistive needs. Thank you.
Thanks very much, Lois, for the nice talk. I don't think we have yet any question coming up, but the one question I have is the complexity of the technology. So sometimes we as engineers, we try to come up with quite a complex solution for a simple problem. But when we talk to our industrial design colleagues, we realize, okay, the need has not been clearly identified. Is that something that you have observed over years between engineers and designers, the lack of maybe communication? I mean, the plenary talk was covering that topic as well, like people with disability not being involved in the process of the design itself. So can you maybe elaborate a little bit on that?
Well, I just want to say that I was very appreciative of being included in this talk. So this is kind of my farewell message. Please pay attention to the users. And there are tools to do it. I once taught a course in which it was an interdisciplinary course with industrial designers and engineers. And we were dealing with vision impairment issues. And the engineers wanted to design something right away. And the students, the industrial design students, would come to me and they would say, they don't really know anything about the users. They don't really know what the problem is. And I would say, well, okay, that's one of the things we have to work on. And then the engineers would come and say, they want to start, they don't want to make anything. They want to watch people. We can't do that. And so I think that there is something in the way we train engineers and designers that separates them according to their strengths. But now we're in a different time. We're in a time where interdisciplinarity really makes something better because we have different perspectives that we bring together. And we're seeing that more and more in projects.
Thanks very much. Thanks very much. I think I like that question to be asked to you because I know you're training both engineers and industrial designers at the same time. So you've seen both in the same classroom. So that was great. All right, so why don't we just move to our next speaker, Dr. Goldie Najat. Goldie is the Canada Research Chair in Robots for Society, and also is a professor of Department of Mechanical and Industrial Engineering at U of T. She's also the founder and director of Autonomous Systems and Biomechatronics Laboratory. Professor Najat is also adjunct scientist at the Toronto Rehabilitation Institute and the Rotman Research Institute at Baycrest, and a fellow of Canadian Institute for Advanced Research. Goldie's research focuses on developing intelligent service robots for applications in health, elderly care, emergency response, search and rescue, and she collaborates with healthcare experts and facilities in developing novel and unique social robots. Really nice stuff, robots and socialization. That's a pretty tough topic to work on. But Goldie's hope is to effectively integrate socially assisted robots into people's everyday life. And she has been invited to speak about her research to scientists, healthcare professionals, policymakers, governments. I believe I've seen the talk you had with the Senate at some point in Ottawa. That I saw actually part of the recording as well. And the general public at many events and institutions around the world, including this very event. We're very happy to have you here, and I think everybody likes to hear how social the robots could be. Thank you so much. The floor is yours. Go ahead.
Thank you very much, Mustafa, for inviting me and for that kind introduction, and the Enable Ottawa Organizing Committee for having me today. So let's talk more about robots. Pedro led the way, and so maybe I'll finish off talking a little bit about how we can use robots to help with our older adults as they age. And we really are focusing on promoting independence and aging in place, really what we want to do. We don't want to move people out of their homes if we don't need to. So we want to develop technologies to support where they are and for them to have overall well-being and aging in where they're used to being, including their own homes. So that leads us kind of to what we've been focusing on, and it's the design of these, what we call socially assistive robots. And what they are is pretty much robots that look a bit human-like, but not exactly. They still look robotic. They interact with people similar to how we interact with each other. So they have facial expressions, they have speech, so they speak similar to us, vocal intonation, as well as gestures. And the idea is that using these robots can improve or maintain a person's overall cognitive, affective, and social functioning. And of course, this goes all within the idea of improving quality of life of our older adults. There's a few different applications we look at, including using these robots to promote engagement in cognitively leisure activities and activities of daily living, to help them complete these activities, as well as keep them engaged in these activities, whether it's one-on-one or in group settings, as well as providing just social interaction or extension of their social network and providing companionship. As well, last one would be safeguarding and providing reminders and monitoring, especially when they're living at home, to make sure, providing assistance in case they do fall, providing reminders for medication. So we've designed a lot of different robots, probably over 20 plus now. We've been doing this for a little while. So I'm just going to go over some of the general applications that we've looked at and then look into some case studies that we've also done. So, for example, meal preparation and meal eating is an activity of daily living that becomes more difficult as you age. Going to the kitchen, finding the ingredients to make a specific recipe or food, and then making sure that you include everything and then go through the steps of cooking it and then eating it, of course, right? And through all those steps, there may be difficulty. You may forget the steps, and even the eating task itself could be difficult. So you may forget, how to actually pick up the food. And so we want a robot to promote that independence, the capabilities to still do these activities on their own, but provide the assistance or prompting that's needed for individuals to be able to complete these activities on their own. And this kind of cohort that we're looking at is usually people who are living with cognitive impairment or dementia. So they have some still limited capabilities and have remembering the task that they need to do and the steps of the task, but can still physically do the task themselves. Other activities we've looked at is clothing recommendation. Here in Canada, as we know, we have our 4 seasons, so it's really important in terms of dressing for the weather, as well as we like to think about dressing for certain occasions. If you're in a long-term care home and your family's coming to visit you, you might want to put a nice outfit on or your favorite outfit. And so the robot can assist you, and the robots personalize their behaviors and their suggestions based on what your preferences are. So we're trying to provide this person-centered care where we take the user into account. As well, we look at activities of daily living, including physical activities such as exercising. These could be through group interactions, group sessions of exercise, or one-on-one. Our reminders included, I think I mentioned already, medication, self-care, anything from brushing your teeth, as well as appointments, using the robot kind of as a Skype on wheels to connect to family members as well as healthcare professionals. especially if you're immobile and can't get to those destinations, let's say, you can use the robot to do that. And it's all done autonomously, meaning the robot has a schedule of when your appointment is, it'll find you and come and interact. And all you really have to do is press a button on the screen and the person you want to talk to shows up. And this helps with extending, especially the social network of these individuals. And then, of course, I mentioned the recreational activities. So we've done test studies with residents in long-term care and retirement homes where they're playing trivia with the robot, bingo, as well as some memory card games. And usually the robot is facilitating these games autonomously. So if we're looking at one particular activity, meal eating, we really went into long-term care facilities and looked at what is the daily life like of a resident living there. And we noticed at meal times, and usually meal times are very specific. 8 a.m. is breakfast, 12 p.m. is lunch, and then dinner is 5 or 6 p.m. And we looked at how, the group was gathering together and eating. And we noticed there's usually 3 different types of individuals. One, people who need assistance physically with eating. The second set that maybe need some prompting to finish eating their meals. And then the third set that can eat on their own. When we targeted that second set of individuals, sometimes they would get distracted from the meal eating. So a caregiver would have to go and remind them, okay, please eat your meal, and kind of focus their attention on the different courses of the meal. And we thought, well, why don't we have a robot help with that? The whole idea of meal eating is that it's a social interaction. You usually do it sitting at a table with other individuals. So we could have the robot prompt and encourage a person through the meal task itself, and then tell jokes and so on, and kind of encouraging statements as it's doing it, because it's a social robot. So we conducted a study where we designed so let me just go back. This is our Brian robot here. And as you can see, it's a social robot in terms of, it looks kind of human-like, but still very metallic looking, let's say. It has a face that displays facial expressions, and then it can use its arms to gesture. Especially in this case, when someone's eating, it can point to the main dish, the beverage, and the side dish. And it has vocal intonation as well. So it gets happy and sad. And we conducted the study where we invited residents to come join Brian for 2 meals, particularly lunchtime, on 2 separate occasions during a course of a week. And we had 5 females and 3 males come and eat their meal with Brian. And they were the older cohort, so they ranged in age from 82 to 93. And we just wanted to see how they interacted with Brian. Number one, this was the first time they were actually seeing a robot, let alone interacting with a robot. So we wanted to see things like acceptance, trust in the robot, ease of use of the technology, which is very important for uptake of the technology. So I just want to show a short video, or clips of a short video, to show you first what Brian looks like, and second, its capabilities.
My name is
so here's Brian waving
nice
and introducing the person,
join me for lunch.
And asking the person to join it for lunch. And then it tells the menu. So you can see it has the gestures. It actually smiles right there when it gives the menu. And then this is a positive encouragement.
I'm glad I get to spend some of it with you.
So, the whole idea that it's social activity, the robot saying, I'm glad I'm spending it with you. And then this is how food consumption would occur.
Helping the food you have there.
So the person would pick up the food from, let's say, the main plate here, and the robot is actually tracking where that food is when it's at the plate, and then when it goes to the mouth.
Who's there?
And it's a social robot, so it tells jokes.
Let us in and we'll tell you.
And then laughs. So the idea here is that we can help an older resident through those steps of meal eating. And if you notice, the 2 steps here are really being able to pick up the food from the plate and bring it to the mouth to eat. And so the robot is tracking that so that the person, for example, doesn't pick it up and drops it or tries to hide it away from the robot. And we do have people trying to trick the robot to see if the robot can catch them in the act. They're really testing the technology as well as we're developing it. So it's interesting from our perspective of, the robot being able to recognize the situation and the person that they're interacting with. And so we wanted to look at user engagement as well as compliance with this activity. And so as I mentioned, we had 8 individuals interacting with the robot. And because of their capabilities, they ranged in having lunch with Brian for 10 minutes to all the way to close to an hour. And we noticed the people who interacted more with the robot actually spent more time with it as well. So we had a lot of interactions back and forth. For example, we looked at, what were they saying to the robot and how much were they saying things to the robot? And we noticed the person that spent almost an hour with the robot had 86 different utterances that they were saying to the robot as they were eating. Whereas, someone who's only 10 minutes had 21, which is actually a lot during a 10-minute interval as you're eating. So it showed that they were accepting the robot during the activity itself. We also looked at, how many times the robot had to prompt them. And this shows, the need for the robot, right, for this activity. So it ranges again from 9 all the way to 28 different prompts needed for the person to help them in meal eating. And of course, we looked at, did they comply when the robot asked them to eat their meal or pick up the food, even take a sip of their beverage. And you can see it's a high average, 87%. Even the one participant who had a little bit lower average was still doing the activity, but in that particular day, one of the 2 days, the meal was eggs, and it was scrambled eggs, and the participant didn't like scrambled eggs. So instead of, when the robot prompted him to eat that, they would just go to the side dish and eat what was on the side dish. So it's kind of interesting, again, for the robot to be aware of that and try to persuade a person to eat, since the main dish is usually the most healthy item on the tray there. So it teaches a lot about our capabilities in designing these robot behaviors in order to have compliance as well. So another activity that kind of stretched from that was, okay, what about meal preparation, the step before meal eating? And this is our Casper robot. And the nice thing about Casper is now that it's mobile. Brian was static. So usually we would put him at a table and people would come sit at the table around Brian. But now Casper can actually come up to you. And this, you can think, can be targeted to retirement homes or people living in their own private homes, where Casper can actually come find you and take you to the kitchen. So Casper is 3D printed. It helps keep our costs down in robot development. And instead of a face that moves like Brian has, it has LEDs for its mouth and eyebrows that display facial expressions. So I'm just going to show you how Casper kind of moves around its environment. So speed this up a little. So here is Casper looking for Derek, our student participant in this case. And so the robot can actively find somebody in its environment to escort them to the kitchen. So here Casper's finding Derek. And then Casper will ask Derek to join it in the kitchen where they can make a meal together. So we designed an app for the robot to help that person actually choose a recipe. So here on the screen, there's 3 different types of recipes. You can have more, you can scroll down. And then it'll go through the steps of actually making, in this case, a tuna sandwich. And you can see the icons are large on purpose. There's very minimal text on the screen so that we make the app user-friendly, especially user-friendly for older adults. So it can help you find the location of the ingredients. And if you don't know where they are, Casper will help you or tell you where they are. In this case, you just have to press the question mark, and everything happens to be in the upper cupboard, which for the sake of the video is pretty quick, right? So then you have all the ingredients. You can watch videos of how to do each step. So if you don't know how to do something or you want to see the step performed, again, you can watch the video to do it. And then you go through all the steps and hopefully prepare your meal. So this allows, the independence of meal preparation, the motivation to make meals. Sometimes older adults may skip a meal. They don't have the motivation to prepare food. So this is a kind of an exciting interaction between a robot that personalizes the interaction for these users. And we've taken Casper to a number of different sites, retirement and long-term care sites, as well as in-lab user testings. And we've looked at, different capabilities and behaviors of the robot that we as engineers designed. And then we thought, well, we shouldn't be the ones designing them. The healthcare professionals or caregivers should be the ones telling the robot what behaviors they should implement, because they're the ones that know the users the best. They interact with them on a daily basis. So we actually had students in our allied healthcare program at U of T demonstrate to Casper, as you can see here in these images, and how to make a cup of tea in a kitchen environment. So the students came in, they had no robotic experience, so they verbally and using gestures went through the steps of preparing a cup of tea, which Casper was able to learn from them and then be able to actually implement through user studies with older adults in the field. So this is a way we can personalize interactions with not just the users, but as well with the caregivers and what the preferences of the users are from the insight of the caregivers. We've done a lot of studies comparing our robots because people ask us, why a robot, why not a tablet? And the main thing is the embodiment of the robot itself. It's 3D embodiment in a real world. It's gestures, it's facial expressions, and it's interacting capabilities that make it more engaging than a tablet. So with our study, we did, Casper here, which has facial expressions, has arms that gesture and wave and so on. And then we did a robot that's just kind of a screen on a base. And then we had a tablet sitting here on the table. And we noticed that users were more engaged with Casper. They had more positive emotions with the interaction itself and listened more to Casper than these other two technologies. So it kind of tells us why social technologies and socially assistive robots are an interesting route to take for engagement and acceptance of the technology. I'll spend a few seconds or minutes on other activities. So those were one-on-one activities. We wanted to see how a group of individuals actually would interact with our robots. So we developed the robot Tangi, and you can see all our robots have different forms, right? We're really looking at what acceptance in terms of robot technology is. So we have different types of robots that go out there, but again, similar to human-like, that they have 2 arms and a head and a face. So here's Tangi, and what we did was Tangi, we developed 2 activities for Tangi, bingo and trivia, and we kind of deployed Tangi in the field in a long-term care facility to facilitate these games. We chose them specifically because they, through prolonged interaction, they do have benefits. They improve overall memory, recall, recognition, as well as motor skills because you're picking up, for example, the bingo markers and placing them on the card. So they do have advantages. And then we did the same thing with trivia, where we built kind of a response board for the older adults that they could put in their response. So when the robot would ask them a trivia question, they could pick A, B, or C, and even ask for a hint for the robot. And in bingo, they were playing individually, but there was usually 4 people playing. And then in trivia, we had groups of 2 individuals interacting with the robot. And we wanted to see what engagement was like between these 2 activities. So we looked at overall engagement. We noticed that it was high, over 90% for both. But of course, trivia, because they're interacting with each other, they were really engaged in the robot's questions because they wanted to win. It's all about kind of winning and your team winning. And in compliance, we noticed, again, the same thing, but the average compliance was actually higher with bingo than trivia. But again, both over 90%. So these show that overall they enjoyed the activity. They had interest in the game, regardless that it was actually a robot facilitating the game, and they had intent to use the activity again. So once the robot was there, we had the robot, for example, there for 2 weeks in each of these sessions. Once we took it back, we asked them, would you use the robot again? And we had high acceptance rates for intent to use, and even the ease of use of the robot, because there's nothing you need to learn new to interact with this technology. It's verbal, it has gestures, just similar to how other humans interact. So there's no learning curve, which is really important as we're looking at an older cohort and those with cognitive impairments. So we have a number of other robots that we're trying to develop, and the overall aim here is to help our older adults with their activities of daily living, provide them with support, and see if we can use robotic technology to even help mitigate some of the cognitive impairments. And as they move through the different stages of dementia, could, through repetition, the robots help them do their own activities on their own, promote aging in place without having to transfer to another home because they need more assistance. And this is what we're hoping to gain. And it's really early on, so we don't know what's going to happen, but we're very excited about our results that, we're seeing promising results in terms of how people are accepting the technology and their performance in the technology. And of course, I have to thank all the students who do the numerous hours of studies. We've had over 200 human-robot interaction studies. So they've, put the robots in vans across the city as well as across the country. They've gone all the way to Vancouver and tested out their robots with all these different older adults and caregivers. I'd also like to thank all our funding partners for contributing to our research and this area, which we find is really exciting for Canada and the world. Thank you very much. I'll stop here.
Thank you very much, Goldie. There's just a very quick question. Someone asked that question from audience. Have you tried, actually the robots that would help feed the people? I know your area of concentration is social assistive, but the question is saying, have you tried, a robot that would physically feed people rather than giving instructions?
That's a good question. There is actually technology that has been developed to feed robots. It's a robot arm that will actually pick up the food and bring it to the person's mouth. So as Mustafa mentioned, we focus on kind of the people who can still feed themselves and need the assistance verbally to do so. But there are now existing technologies that can physically help with that task as well for the other individuals that have lost their capabilities, especially physically, to do some of the tasks themselves. So you can kind of combine these two. Eventually, you can put that robot arm onto one of our robots and it can do both tasks.
All right, thank you so much. I think we're getting a little late with our panel discussion, so I'm going to go right away to our next speaker, Dr. Chen. Jun is an assistant professor in the Department of Bioengineering at the University of California, Los Angeles. His research focuses on nanotechnology and bioelectronics for energy sensing, therapeutic applications, and so on. And all in the form of smart textiles, wearables, and body area networks. His work was selected as research highlights by Nature and Science and covered by world mainstream media such as ABC, NBC, CNN, Wall Street Journal, and many others. And he was also recognized by the 2020 Altmetric Top 100, Top 10 Science Stories of 2020 by Ontario Science Center, and 30 Rising Leaders in Life Science by Informa. Also, as Emerging Investigator, he received Emerging Investigator Award and many, many other awards and recognitions that I think it would be too long for us to cover all of those. But beyond research, John also serves as the Associate Editor of Biosensors and Bioelectronics Journal, and one of the interesting research projects that he directed, and that was actually the reason that we got connected and we brought him over here, was the glove, the smart glove that translates the sign language to text that helps people with disability. So here we go, John, you're the last speaker for today before we start the interactive sessions. Go ahead.
Okay, let me unmute myself first. Thank you very much for Mojitaba's kind invitation and last introduction. Yeah, here I just wanted to share with you guys one piece of our recent research work on wearable center-speech translation. So because I only have 7 minutes presentation, so I just prepare 7 slides. So generally, basically, I'm an assistant professor in the Department of Bioengineering at UCLA. And as we know, actually, 37.5 million Americans 18 or older report trouble hearing. So this data from is for a group of USA people. I think the trouble hearing probably is a commonly shared problem around the world. Actually, due to the lack of effective communication tool between center and non-center, so because the previous developed technology, they are very heavy and sometimes inconvenient to wear. So with this concern, very recently, we developed very soft and lightweight glove. So when you wear the gloves, we use perform standard American Sign Language. So this kind of glove can first convert this kind of mechanical motions, including the facial expression, this kind of biomechanical motion into electricity, because those sensors are very sensitive to convert those finger spelling or other mechanical motions into electricity. Then we can use the electric signal and to translate them into voice and display as a cell phone app. But how to do that? The first step is that we need to develop some lightweight sensors which could be responsible to convert finger spelling or other sign language component into electricity with a high sensitivity. So here is our working mechanism. Basically, we are very young, we're educated that when we glass to friction with silk, it can generate static charge, especially in Canada. It's very cold region. In cold winters, when you take a sweaters, you can see the sparkles in the darkness. Actually, those because of contraindication, or sometimes in the winter when you use a keys to open your car door, it get electrified. All of those because of contraindication. Actually, contraindication is very old phenomena in our daily life. Actually, in the scientific community, we definitely have a table which describe different type of materials have different electron affinities. So, for example, human body, the human dry skin has strong ability to lose electron, get a positive charge. Some of the fluorine polymer or silicon or or polypropylene, those kind of polymers have strong ability to grab electrons, get negative charge. So that's why we glass friction with silk, because those glass and silk have different electron affinities. When they contact each other, transfer the interface with the result, glass will be positive charge and silk will be negative charge. So just based this on working mechanism, this phenomenon, in 2012, we invent fundamentally new technology which could be sensitively convert biomechanical motion into electricity. We call it triple electric nanogenerators. That's TNG for short. How does it work? Basically, when two polymer materials, for example, the blue one and the purple one, when there's biomechanical force, when the two contact with each other, transfer the interface with the result. One will be negative charge, another will be positive charge. So those charges are static charge, can sustain for the polymer surface a long period of time. So if we deposit a pair of metal electrode, that's the yellow part, on the back of the two polymer layers. So when there's a biomechanical force to induce a periodic contact separation between the charged polymer membranes, then they will generate alternating current in a internal circuit. So you can say this technology could be very lightweight because the polymer layers only usually is based on a surface charging effect. So the polymer thickness usually is below 20 micrometers for each layer. So the total thickness of the device could be controlled under 50 micrometers. Consider the metal electrode usually just 100 nanometer thickness. That's good enough to make them conductive. So that's 20 micrometer plus 200 nanometers so the total thickness could be controlled below 50 micrometers for this type of device. So you usually just thickness of human hair, diameter of human hair. So you can say this technology certainly has a number of advantages, as I list some of here, because these have very simple structure and a lot of soft materials can be involved here, because almost all of the material around us has itself electron affinity. As we employ two types of material with different electron affinities, then we can use them to fabricate a triple nanogen, convert biomechanical motion into electricity, and also it's very lightweight, low cost because they have very simple structure design, so the manufacturing cost should be very low. Second, the polymer materials we use here generally are economically available, so the materials cost also very low. So to make this core technology very cost effective. So with this working principle, so we develop a wearable glove which could perform sound-to-speech translation. How does it work? Basically, these two gloves have two components. These gloves have two components. First is a stretchable sensor unit. This is responsible to convert the finger spelling, this kind of biomechanical motion, into electric singular accordingly. And they also have a second component, that's a wireless flexible PCB, that is principal circuit board, so which is responsible to process this generated data, convert them from the generate electric signal from analog electric signal to digital electric signal, and also we use some machine learning and to enhance the translation robustness. So let's look at the first component, that is a stretchable sensor unit. That's basically this stretchable unit, as I mentioned previously, is responsible to convert this kind of finger spelling, this kind of biomechanical motion into electricity. How does it work? So basically, the working principle is the triple electrical analogy that I introduced in the previous slides. Because you can see we can start this kind of stretchable fiber starting with a rubber fiber as a supporting substrate, because this rubber fiber is very thin and also it could be stretchable. So then we coated this kind of, we use this kind of polyester mixed with metal yarn, this kind of hybridized yarn to twist against the rubber. And the outer surface, we have our layer of PDMS polymer as a shell to form this kind of core shell structure design. So how does it work? Basically, when this kind of fiber gets stretched, so they will induce the contact substitution between the PDMS and the polyester. So because PDMS and polyester are two types of polymer which have different electron affinities, so charge transfer the interface with the result, PDMS will be left charge, the polyester will be positive charge. So when we keep this kind of finger spelling, because this stretchable sensor is tightly attached to the fingers, so this kind of due to when we perform American Sign Language, so those kind of stretchable sensor could be stretched and to induce a contact error change between the polyester and the PDMS, and with eventually they will generate electric signal in an internal circuit. You can see by doing this, we can convert this kind of sign language component into electricity. So here are the electrical patterns generated accordingly when we perform standard American Sign Language. For example, we express the letters A, B, C, I, L, Y, or this kind of numbers 1, 2, 3, 8, or some short phrase, for example, I love you. So you can see those are generate electric signal from the 5 fingers accordingly. So we can use this kind of generate electric signal as the singular patterns, and then we take a further step to convert or translate those electric signal patterns into sign language. So basically, while this text gloves and when we perform American Sign Language, so then this kind of American Sign Language could be converted into voice by using cell phone app. And here are the two user interface. So on the cell phone app, so we perform American Sign Language. So then the cell phone app could be display this hand gesture accordingly, and also those are generate electric signal from 5 fingers, just like the electrical patterns here. So definitely this technology could promote the communication between sender and non-sender, and especially could be helpful to the people who wanted to learn sign language. So here is a video I wanted to show to visualize its operation its procedure. So probably I need to show my computer sound first.
I, L, Y, I love you.
So basically from the video, we can see that when we perform basic American Sign Language, then when you bring out your cell phones, the cell phone app could translate into voice and display the voice. So it's definitely, even when you don't understand American Sign Language, definitely this pair of gloves can help you to promote this kind of communication between sender and non-sender. So recently, this work received a number of media coverage in the world, and also highlighted by Science, and also is set as the top 10 science story of 2020 by the OSC, this in Canada, a center in Canada. So, and also is set as a 2020 top 1 automatic top 100. That is the top 100 among of the 30.4 million works in 2020 across 20 subjects. So I think that's much of our the work I want to share with you. And due to a time limit, so I still put my contact information here. And in case you don't have time to ask me question, but if you wanted to have some question for me, you can shoot me an email. And also I have some social medias as well. And those are pathways that you can reach me. And welcome you guys to Los Angeles, the city of angels. And thank you very much for your attention.
All right, thank you very much, John, for your nice presentation. It was great to see that. Not sure how much we have time for many questions for our panel, but maybe a quick question for John. I think the sign language is involving both hands. Have you worked on the coordination of both hands as well?
Yeah, this is a very good question. Actually, the review asked us the same question. So first, I concede that this very rough of a first proof of concept demonstration for our sign language, but also we also place our sensors into our facial and also in our eye bones. Those are some body part which could contribute to a sign language component. We try that. Those type of we use this kind of stretchable sensor can also sensitively convert this kind of sign language component into electricity, and we show that we test that in a lab scale demonstration. Basically, we test 660 sign language component. Actually, the translate accuracy is about 98%. So I think this kind of translation robustly and accuracy could be further improved in the future. Yeah.
Okay.
Yeah.
And I guess you're using the classical machine learning like a black box thing to convert the signals to actual speech.
Yeah. Yes. We use a very basic machine learning algorithm, but definitely those software components definitely could be improved for the future. In the future project, we will use more advanced machine learning algorithm. So far, we just use the SVM, the super vector machine. Actually, this very old traditional language processing algorithm in the community.
Okay, thank you so much. I don't think we have more than a few minutes, but there was a comment regarding the talk by Lois that one of the audience was happy that actually you talked about inclusion of people, or the users basically in the design process. I wonder if anybody else wants to comment on that or not. Well, I think you're mute, Lois.
Unmute myself. Okay, there we go. I just want to say that this past winter we worked with the Abilities Center Ottawa. And one of the things that I really appreciated, and I think my students did as well, was their motto. And it is nothing for us without us. And I just thought that was not just, okay, we know what we're going to do, we're the experts, but we're actually going to involve you as much as possible in the process. And that's fantastic. Just wanted to add that.
If I may add something, I really believe that the user should be at the center of all the design process when we're talking about assistive technology, which is quite a challenge when we are developing robots for kids, because we need to find ways of getting their opinions, of understanding what they would like a robot to do and to look like, etc. But there are some very successful methods to collect the opinion of kids, and for sure the user should be at the center of the entire design process.
Okay.